We are now going to study section 1.4, Proofs and Theorems. And within this section, we are studying back within logic, and we're going to develop our system of logic, as well as we're going to define theorems and define theorem calculation or proof, which will help us to prove theorems. So essentially, the theorems will become our mathematical truths, and the proofs will help us to prove these mathematical truths. So the learning outcomes for this section are simply to write theorem calculations from gamma, or equivalently we'll learn how to write gamma proofs, or equivalently Hilbert proofs. So we know from our last set of videos that gamma stands for a set of well-formed formulae. So these are essentially going to be our assumptions that will give us our relative truths within logic. Okay, so we'll explore that a little bit later. Before we get into developing our logical system, we need to more formally define schemata, which is plural for schema. So the term schema has come up before in previous videos and previous classes, and it's helpful for us to formally define what this is and then elaborate on how we are going to use them within this section and also how we used them in the previous section. So recall, a schema is simply a string over the following augmented alphabet. So it does include our Boolean alphabet, which we denote by the script V, but we add to it, so the union of this plus these symbols, so the set of these symbols, the close brackets, the colon, and the equal sign, which you'll recall we used in the last video to define substitution. So we used a schema to help us to define the operation of substitution to represent that. Okay, plus we're going to add to this our syntactic variables. So our string variables and our meta variables. Recall that all of these stand for different strings within our Boolean alphabet, and these bold P, Q, R, for example, are meta variables, which represent any possible Boolean variable in the schema in which it appears. So recall, we saw schemas last class when we were talking about tautologies. So oftentimes we developed a schema involving string variables, which we would then replace those string variables by Boolean variables or well-formed formulae to represent a well-formed formulae and determine whether that schema was a tautology or not. So the idea here is that we want to use the schema to represent many different types of well-formed formula that have the same syntactic structure as given by this particular schema. So a schema stands for infinitely many different well-formed formulae which have the same syntactic structure, and we're able to determine whether well-formed formulae of those syntactic structures are tautologies or not. In the case that they are tautologies, we simply have a finite way to show that infinitely many different well-formed formulae of the same syntactic form are tautologies, and in the case that they aren't tautologies, then we knew that we needed to come up with an instance of a schema to identify when that schema was not a tautology. So identify a specific well-formed formula that wasn't a tautology. So to summarize this, essentially within the schema, we want to replace all syntactic variables with any formula or Boolean variable, and we obtain a well-formed formula. So essentially, a schema is just meant to represent infinitely many different possible well-formed formulas, where we can replace any of those syntactic variables, either the meta variables by Boolean variables or the string variables by other well-formed formulae, to obtain a specific well-formed formula. And this formula would be an instance of that schema. So we can either show that syntactically, we have infinitely many different well-formed formulae that are tautologies that are of this syntactic form, or we're focusing simply on the Boolean connectives which make up that formula. Or we discover that the well-formed formula of this form are not automatically tautologies, right? So it depends on the meaning behind those syntactic variables, and so we can identify an example of a formula or an instance of the schema which isn't a tautology. And we'll see that we'll apply this next class when we look at tautological implications as well. We're also going to need to use schemas, or we're going to see schemas as we develop our logic. And the reason for doing this is to help us to make finite the number of assumptions or axioms that we're going to have. So you'll see that we're going to continue to use these schemas, which represent infinitely many well-formed formulae, to help us to make simpler, to find a shortcut for stating theorems. Right? So we want to generalize using schemas all of the forms or syntactic forms of well-formed formula that are true.